Okay, good afternoon, everyone. It's my good pleasure to be here. So thanks for inviting me and for hosting me. And thank you, Angela, for your nice introduction. My background is applied mathematics, and particularly in instabilities and transformation in soft solids. And today my topic is about instability, surface wrinkling in film substrate bilayers. And I'm a postdoc in University of Oxford, working with Professor Wentzel-Kramers-Brillouin and also working with Professor Mihai. It takes a long time for me to find a good starting point, actually. So I think I would like to start with an example that you might be familiar with and be interested in. So I think brain is a good starting point. This is a picture of the human brain, and for a long time, it is believed that the size or the volume is the most important thing for brain. And with a comprehensive understanding of the brain development, nowadays we know that the specific pattern of the brain is very critical. And here I show this is the gyros and circles. Gyro and circle. This is gyros and this is circles. And we know that it creates such a very interesting pattern to increase its surface area. And but not only for this reason. To be honest, for different people, the pattern is not exactly the same. But for a specific person, they must have an optimal one. Any change in the patterns, in the geometries will generate certain disease. So it's very important to understand why it forms like this and how can we do to understand the formation of such patterns. And we know that this pattern is responsible for the intelligence, for your memory, the cognition, also your memory ability, consciousness, a lot of things. When you cut this, okay, cut the brain, and you will obtain a similar picture like this. And actually, this part is, okay, I cannot touch it, sorry. The top, okay, it's not works. This is the circles and this is the gyros, okay. And when you neglect the geometry, the curvature first, and you neglect this, and you can reproduce the similar transformation from either experiments and numerical simulation by using different models. Something like this. Okay, this is from experiments. You can use the swelling of polymer gels to create such pattern, and also you can use some finite element simulation to simulate this. So it can be reproduced. Also, if you further consider the curvature, you will also, generate a very similar shape. This gives us much confidence to use some mathematical modeling or mechanical modeling method to understand the formation of brains. We know that this is the formation of brains, and another question is that when it forms like this, okay, we want to understand the evolution of the morphogenesis. People studied this, okay, and the half period of the gestation, for instance, from week 22 to 23, when you try to get a picture of the brain for infant. So you know that this is the surface. It is almost smooth, right? With time going, you can see that, and some very special period, very small wrinkles or some specific patterns occur. And with further evolution, you will have the final patterns. This is not only the only example in nature that such process happens. Another very interesting example is that for the pumpkin, the newborn pumpkin, you can see that the surface is almost smooth. And with growing, and to a very special moment, we have the surface wrinkles, and it will fall its way after the following days. Also, I aspergillus. This is aspergillus for cats. This is aspergillus for human. You can see that there are different patterns inside. These patterns are very important to maintain its normal function. And this is the stomach. You can see there are zigzag patterns inside. So from this example, we know that there is a fundamental fact. First, you have initial geometry. From the viewpoint of mathematical modeling, you have an initial geometry. And then the geometry is changed, driven by growth or some other chemical reasons or biological reasons. In this process, stress is created. And stress will further regulate and change the state. And at a special moment, you have pattern formation, a specific pattern formed in your geometry. And then you have the pattern evolution to reach the final pattern you observed or you know in nature. So such a process actually is very, very similar to a very classical engineering problem. We call it the Euler instability or Euler buckling. So, for instance, if I have a paper, okay, very thin paper, when I compress it, it is easy, it can bend, right? Very easily. It means that the paper is very thin, so it cannot support any compressive stress. It cannot support compression. But when you have many papers, definitely you need to use when you first impose a very small force, okay, it can support some certain compression, and then and a special moment under critical load, it will bend. So let's model it in mathematical way. You have such a beam, a very simple structure. It's a 1D model, and you impose some compressive force. As a side, there exists a critical force, F critical. When the force is less than the critical force, you will maintain the geometry. When the force is over the critical force, you will have a buckled or a bent structure. And this is the Quebec Bridge in Canada. It's very famous because it's the most commonly used failure example in engineering mechanics. At the time it's designed, it only considers the strength of the beam. So the designer doesn't consider the instability of the beam. So although the strength condition is satisfied, but it still break. It still broke because of the instabilities. Go back to the Euler's time, actually. Euler already found a very nice solution for this problem. Okay, so he derived a beam equation. We call it the Euler beam equation. And the EI is the bending moment, is the ability to support the bending deformation. And the M is moment imposed in the two ends. So here, this W is deflection. It measures how far it is away from the center. And we have a very simple ODE, a second order ODE. And you can rewrite this equation as in this form. Here the K squared is definitely a positive number. And I think you know how to solve it, right? We can write down the general solution of this equation. We have two undetermined constants, C1 and C2. And further, we need to impose some boundary conditions. For this one, we know that for the two ends, the deflection is 0. So we have the boundary conditions. W0 and WL is 0. So we obtain such a very beautiful formula. When you look at this equation, you know that absolutely 0 solution. W0 is a solution, right? We call it the trivial solution. And this formula tells you when the F reaches this value, this equation has a non-trivial solution, has a non-zero solution. So this is a very famous, This is a very famous Euler formula and derived in 1744, okay? Almost 270 years ago, 80 years ago. And from this, we know that actually to identify the onside or the threshold of instability is equivalent to solving an eigenvalue problem of ODE or PD, right? This is the main mathematical insight into this problem. Following this standard way, we will know. First, we want to apply this to the biological or soft systems. The previous example is for classical, hard materials. It means that the strain is very small, less than 1%. But for soft materials, okay, there is a long-standing, typical model, a film bonded to a substrate. Especially the film is very stiff, and substrate is very complete. And if you compress the structure, the compressive stress can be generated by either compression, different swelling, heating, a lot of loading scenarios. And you can use this to study different instabilities. And for soft matters and biological tissues, you need to consider finite deformation because the deformation is not small. The soft matters are very soft, so their modulus is very small, so they can undergo large deformation with small force. And you need to consider that the material is nonlinear. The stress-strain relation is nonlinear, and also the geometrical relation is nonlinear. The strain and displacement relation is also nonlinear. Okay, so you have initial geometry. Okay, we call it the reference configuration, and it can undergo a finite deformation to form a new configuration, VR. And in this, this is a finite deformed configuration, but there's no instability. If you want to start instability, you can superimpose an infinitesimal deformation to create a final deformation, and because this is an infinitesimal deformation, we call it the increment theorem. Because from this configuration to this configuration, the displacement is incremental. It's very small. The magnitude is very small. Okay, for this, we know that we have some nonlinear elasticity framework. There is a systematic way to deal with instability problems. In subsystems, we know that there are many different parameters. We have the different moduli, different thicknesses, and also we have different loading parameters. And for this structure, because the film is very thin, so sometimes people just regard this as a beam. You can use some beam equations to model the film. And also you can replace the substrate by the weaker foundation, an area of springs. It means that you only consider normal force and you neglect the shear force. But these methods are very effective in some time, but sometimes it will generate errors because it is not self-consistent mathematically. To do it in a mathematical consistent way, we can start with the continuum mechanics. We impose some proper constitutive relations or string-ended functions, and you can select proper configurations that you are interested. And then you derive the equation of motion or the equilibrium equations, impose some proper boundary conditions, and then there is a y-imposed boundary value problem for you to study. And you can solve the eigenvalue problem to determine the onside of the instability. Or you can carry out a weakly nonlinear analysis to derive the amplitude equation. And also you can start with this and directly solve it numerically to do some finite element simulations to extend the solution to the strong nonlinear region. And there are two reference books in this field. The first one is by Professor Ogden, written 40 years ago, and the second one is by Professor Gorelli, and this is a new one. And then I want to go back to my topic, right? Because my topic is about wrinkling in bilayer structures. There are two cases. The first one is a planar case. And consider that this is your skin. When you compress your skin, definitely you will see wrinkles, right? This is caused by the external force. Of course, with aging, naturally you will deteriorate skin. It means that the force condition is maintained, but the material property will change. Also, when you take a shower when the time is long enough, you will find that, okay? Because of the dehydration, in your finger, there will form very, very, very beautiful wrinkles. And when you look at the structure of the skin, it consists of epidermis, dermis, and some fats, okay? And usually, the epidermis is stiffer than dermis in order to protect your side. And the elastic properties will change due to position because of the existence of the microstructure. So actually, it's not a homogeneous body, but it's an inhomogeneous or graded body. It contains the graded modulus. So to study this, and the second is the curved case. Okay, when you look at the elephant tracks, this is Asian elephant. This is African elephant. You will find that there are many wrinkles around. The wrinkles actually is not only a result of the instability, but it also maintains a function. For instance, it will allow the track to elongate 40% to its original length to achieve some functions. And when you look at the cross-section of the track, there is a hollow part because you want air to pass. And also, you find that the radius of the track is changing along its length, causing that there are different wrinkle numbers. For instance, in this part, it has a large radius, but small wrinkle numbers with large wavelengths. And in this part, you have more wrinkles, but the wavelength is small. This indicates that the wrinkle number along the track is varying as the curvature changes. So what's the essential role of curvature to regulate the pattern formation? It's deserved to be investigated. Okay, for the first part, we start with this model. We have a stiff film coated to a substrate. And the substrate is graded. It means that the shear modulus of substrate varies along the thickness direction. It's a function of the x2. And also, we assume that both materials are incompressible. It means that the volume will be maintained during the deformation. And when you look into the deformation process, you have an initial configuration, and then you impose compression. This will induce a homogeneous deformation. And when you further compress it, a wrinkled state will be formed. And we take a point from the structure, and we can define the position vectors. The big I's is in the initial deformation, and the small x is in the current deformation. And then you superimpose, according to the increment theory, you superimpose the small deformation to create the wrinkled state, and we have this x tilde. And we know that their relationship is given by this. And we use a very simple model, the New-Hawking model, and mu is the shear modulus, and lambda 1, 2 are the two principal stretches. Because this is a planar problem, we consider a plane stretch problem. So the stretch in the third direction is imposed to be 1. So there is no deformation in the third deformation, in the third direction. Okay, so we can identify the homogeneous deformation. It's very simple. So this is the deformation gradient. It's a diagonal form in lambda 1 and lambda 2. Because it is incompressible, so the determinant of f is to 1, so we must have this. Lambda 1, we can denote this by lambda, and lambda 2 must be the inverse of lambda. And then, this is the relation of the coordinates in the initial deformation, initial configuration, and the reference configuration. And the deformed thickness is determined by this. It's a very simple algebra, actually. And this is the definition of the nominal stress and the Cauchy stress. You can derive this, and then this is the force equilibrium. Actually, for homogeneous deformation, because the stress tensor is constant, so this is satisfied automatically. You don't need to solve this. And how can you solve this P? Because the P is a Lagrange multiplier enforcing the incompressibility. So you can solve this from the boundary conditions. For the top surface, we consider that it's free, so it's traction free. And for the, because we consider a half space, so and infinity, we consider zero displacement. And at the interface, we impose the continuity condition. It means that the traction and displacement are continuous across the interface. From this, you can solve that the Lagrange multiplier has this form, very simple. So then we can obtain an analytical solution of the homogeneous deformation. Then we derive the incremental equations. This is our starting point. Okay, so for small magnitude of the displacement, we can expand the incremental stress. This is stress from the current configuration BR to the wrinkled configuration BT. And this is the first order Taylor expansion. We only maintain the linear terms. And here the JILK is elastic modular. We can obtain this by this form. The incremental equations are then derived in this. There are two. The first one is the force equilibrium. The second one is the incompressibility. And we have the boundary conditions. Okay, traction free, zero displacement, and the continuity condition. Actually, here the hat means that this is the quantity evaluated in the field. So the U1 hat is the displacement of the field. Okay, now we have a well-imposed mathematical problem, a boundary value problem. And now we need to carry out the bifurcation analysis. Look at this, okay? You can see that it's sinusoidal waves, right? So we can look for a triangular wave solution in this form. And then, because the substrate is graded, we impose, this is an assumption. We assume that the modulus is changing exponentially in the substrate. So we have this. Mu0 is a constant, mu1 is constant. Actually, mu1 is modulus at infinity. And to the top surface of the substrate, the modulus should be mu0 plus mu1. If you just plus x2, x2, h0, you will obtain this. And you can just substitute these solution forms into the equations and eliminate, for instance, u and p in favor of v. Finally, you will get two equations, one for substrate and one for the field. Okay, first order linear ODEs. But note that because the mu is here is a function of the x2, this equation is not an equation with constant coefficients. It's an equation with variable coefficients. And here this k is a dimensionless wave number. Okay. Now we have some parameters I want to emphasize. First is parameters R, gamma. Gamma here is what? Is modulus ratio of the field to the modulus and to the top of the substrate, mu h. And second is the modulus ratio of the modulus and infinity, mu infinity, by the modulus ratio of the substrate on the top. And here alpha is a dimensionless decaying coefficient. It controls how fast it decays or increases exponentially. And lambda is our control parameter, is a compression, is a stretch. H0 is the thickness of the field. And we can use determinant method, compound matrix method, strong method, etc. to solve eigenvalue problem numerically. And this is the bifurcation curves. The parameters are given here. Gamma is 100 and beta is 0.01. It means that the film is very stiff than the substrate, and the modulus in the substrate is decaying exponentially. So look at this, okay? This is a function of the stretch, lambda, as a function of the wave number k for different values of the film's thickness. Each point in the curve is a solution of the bifurcation condition, okay? But we need to identify which is the critical state. Suppose that this is lambda x to 1. In this value, there's no deformation. You load from this value, and then use compress it. So we know that the blue points actually gives you the maximum points of each curve. So it means that when the loading curve intersects with the bifurcation curve, we will observe a bifurcation state. So the blue points determine the critical states. We call it the lambda critical and the K critical. And because they have the maximum stretch or the minimum compression, so they are analytically favorable. And from now on, we will only focus on the critical state. The previous curve is obtained by numerical techniques. And when we look into the equation here, and when you consider that the film is very thin, it means that h by l is very, very small. In this region, we know that wave numbers are large. That means that the k is the large parameter, right? We have large parameter in our equation, so we can resort to some perturbation method to solve it approximately. Then we look for a solution with this form. Here, S is an extension in terms of k. Then we substitute this solution form into the equation. And we find that there are 4 different equations of the S. We call it S1, 2, S3, 4. Then the general solution of V is a combination of the 4 solutions. So we have a general solution, an analytical but approximate. Then we just substitute the solution into the boundary conditions. Note that for the film, we have the exact solutions. So we will form a matrix times 8 coefficients to 0. If we want to obtain a non-trivial solution, we need to require the determinant of the I equal to 0. So we have an approximate bifurcation condition. Actually, it is purely an algebraic equation. But it is very complicated to be solved analytically, actually. So this is a comparison between the approximate bifurcation condition and the exact one. You can see that in the large region, when k goes to infinity, the agreement is extremely good. Even for k is not that large, 5, 4, 3, we have good agreement, right? So it means that this is a very good starting point to pursue some analytical solutions. Then we consider the case. First, the decaying rate is not large, okay, and the modulus is decaying fast, is decaying in the substrate. It means that the top surface of substrate is stiff, but at the infinity is very soft. And this is the bifurcation curves obtained from the numerical techniques. And we know that the bullet point gives us a critical state. It means that we can use this. The first one is bifurcation condition. And the second one is you just need to take the maximum point. So from the 2 equations, you can obtain the lambda critical and the k critical. And the small parameters are we consider that H is very small, very thin film. In this case, we know that the string is very small. You can see that. This is very, very small, around 2%. And the film is very stiff, so gamma is large, k is large. So we have 4 small parameters. We need to make an order analysis. First, from the leading order balance, we know that in this case, epsilon is of order gamma minus 2 epsilon is of order gamma power 2 minus 2 by 3 in this order, and kh0 is also small. In second order balance, we have this. Okay, we have different orders, then we can seek a solution in this form. And then substitute the solution forms into the equations, and you can get this. Okay, it's not very beautiful, but it's not bad. We must mention that when beta x to 1, the girded substrate reduces to the homogeneous one. So it means that we don't have these terms, and we found that this actually recovers the classical equation, classical solutions accurately. And also, in this case, because we know that gamma is actually this order, right? It means that it's very, very large. If H0 is a given small parameter, this is very large because the power is minus 3 by 2, right? Also, we consider that gamma is not that large. It can be power minus 1 or power minus half. So we want to see what happens. It means that when the film becomes softer, not that stiff. Okay, in this case, we have this. Gamma is of this order, and we can derive the case of this order. And we have these equations. Okay. Also, when you let beta is to 1, it will recover the classical solutions. And for this case, gamma is not that stiff. Okay, we have this. In this equation, you will find that you cannot say alpha and beta. Notice that alpha and beta is the parameters related to the gradient modulus. It means that gradient modulus doesn't make any sense in this case. And let me summarize this. Okay, we want to identify the order where alpha and beta first occurs. This means that at least in the leading order, it doesn't make any difference. So it's a minor factor. And when gamma becomes smaller, first it appears under the second order in both for lambda critical and K critical. For the second case, it occurs under the third order. It means that it goes to the higher order. For the last case, actually it disappears after the truncated order. It means that it makes no difference. So we conclude the influence of the gradient modulus will shift to higher order as the film becomes less stiffer. So this is a very important observation from the solutions. And also this is validation with the exact solution. You can see that there is very good agreement. You cannot see any difference between the two, the dashed line and solid lines, for the critical stretch and for the critical wave number. And also we consider that for the previous case, the modulus is decaying in substrate. But for this case, we allow the modulus to be increasing in substrate. And we have this solution. And in this case, unfortunately, we cannot solve it exactly. We use the fitting method to find such a actually it is very ugly, but it's very useful expressions. You can see that the modulus ratio and alpha beta both occurs in the leading order, and it affects the critical wave number through the log term. It means that it makes a very big difference. You can see that when you increase beta, and there is a very big difference. So in this case, in the previous case, the gradient modulus doesn't make sense actually. The structure cannot see the gradient modulus, but in this case, it makes a great difference. So you need to consider the gradient effect. Okay, for second part, okay, maybe I need to speed up. And this is a picture. Okay, we want to model this, and we assume that it is cylinder. Of course, it's not a very accurate, but this is the first step. Try to model the elephant trunk, and it can grow. And in this end, we impose the spring condition because we found that it must generate more compressive force to induce any instability. And the outer layer usually grows faster than the inner layer, so there is a differential growth between layers to generate the compressive stress. And for the finite growth theory, I briefly introduce this. Okay, we only need to decompose the deformation gradient into two parts. The first part is G is the growth part. It means that it will grow, but grow freely without generating any stress. And in order to satisfy the compatibility condition, you need to impose an elastic deformation. The second part, A, the elastic deformation gradient. Okay, finally you have the final part. This is growth theory, most commonly used in the field now. And we have this. For our model, we have a bilayer tube, right? Gradient bilayer tube. And the S means the skin is outer layer, M means the muscle is the inner layer. And this is the growth tensor. We know that the skin, there is an additional parameter gamma here, means that the skin can grow faster than the muscle. G here is a pre-growth factor. and we can derive the solutions for the perimeter deformation. Here, I emphasize that the deformation is not homogeneous, but is asymmetric. So you can also derive the solutions analytically. And you can also derive stress. The only non-zero stress is the sigma x11. One is in the direction of r direction. And you have the resultant axial force. And this is because it is attached to a screen. This K is the stiffness of the screen. Right? This is the force balance in the third direction, in the axial direction. And also we use the incompressible Newton model, very simple, right? Mu is the shear modulus, and here beta is the shear modulus ratio. And I give an example for the stress distribution. You can see that for the given parameters, this is the muscle, right? The muscle is actually, under compression, but not too much. But the skin, you can see that the stress, sigma 33 is the stress in the axial direction, is very large. It is compressed more. That's why it will form wrinkle at some stage. Okay, and here we use the straw formulation and the surface impedance matrix method to numerically solve the eigenvalue problem. And I don't want to show any details, I just to show some results. This is a bifurcation condition. We have the different parameters, modulus ratio beta, different growth gamma. With number n, the pre-growth g, R0 is the inner radius of the muscle, and R1 is the outer radius of the muscle, and H0 is the thickness of the skin, K is the stiffness of the spring. This is the target geometry. So this is the eigenshape of the wrinkle state. And we have this. First, we show the gamma as a function of the wave number. You can see that actually in the growing case, the minimum point is the critical state. With different values of the pre-growth factor G, we have different values of the critical factor gamma. And also with different modulus ratio, you have this. So you find that they all have a minimum point. This is our critical point. And okay, then we try to change the modulus ratio. Okay, in this case, the stiffness of the spring is 20. Okay, this is the dimensionless parameter, and you will find that when you increase the beta from 65 to 33, you can see that the ring is shrinked. It means that when you further increase the stiffness ratio, beta, you cannot see any solution of the gamma. Then we examine this bifurcation condition as a function of the gamma when the wave number is given by 12. You can see that the minimum point we go here, the dashed line is 0. It means this is a bifurcation condition. Right here, this bifurcation point. It means that when you increase beta, this will never have intersection with the zero line. So it means that bifurcation curves will disappear, and the critical condition is that, okay, from this bifurcation equation, when the minimum point is exactly the bifurcation point, and in this case, it means that it shrinks to 1 point. So we have 3 equations, we can solve this, and we determine this. Okay, for given k, we have different values of the beta max. Over this beta, you can see that this is smooth region, means that there's always no wrinkling. It's always smooth, and in this wrinkling will occur at a special or critical growth. And I just want to enlarge this part because you can see that when k goes to 0, it means that it's a free end. If free end, it means beta is very small. That's why when you consider that beta is slightly larger than 1, you cannot observe any wrinkling. That's why we need to impose an additional spring condition to generate wrinkling. When k goes to infinity, it means that the tube is restricted in a box. So beta max will go to infinity. So you don't need to worry about the values of beta. Now we want to show the effect of skin thickness. Okay, you see that with a thicker skin, it increases the critical value for wrinkle, but but it will also reduce the wave number, right? The wave number is reduced, is a monotonically decreasing function of H0. Then we examine the effect of the muscle thickness, the R1. Typically, you find that R1 has no influence on the critical wave number. This is not surprised because actually the structure undergoes a surface instability, so it cannot see the difference of the thickness of the substrate. It is equivalent to the infinite substrate, so it has no influence. But we found that with increasing R1, it will make an early instability because the gamma critical is lower. Then we consider another case. We just keep the thickness ratio. The H0 by R1 is fixed. And we want to see what happens when the curvature is changing. Okay, it means that it is found that there is a non-monotonic curve. It means that this is not surprised because in the previous two cases we know that H0 will delay instability, but R1 will promote instability. So there is a competition between them. Then there is a minimum. But the wave number is monotonic, right? With larger curvature, we will always have a lower wave number. And finally, this is the effect of the modulus ratio. And this is very typical because we know that with the stiff skin, with the stiffer skin, we will always have an earlier instability, but with lower wave number. That's why we check this. Because gamma, the growth factor, is not that enough to have physical meaning. So we check the length that it changed. This is actually related to the force, because this is proportional to the force generated by the spring, right? You can see that it is increasing, but the wave number is decreasing. Finally, we use because this is also an eigenvalue problem with variable coefficients. So we deal with this with the WK approximation, and this is the comparison between the approximate solution and the exam solutions. To be honest, you cannot identify the difference, right? Very, very good approximation in different parameter regions. And from this, we consider two different cases. First is that the modulus ratio is not large. It's of order 1. In this case, we have two small parameters, H0 and the 1 by n, and the wave number. Okay, and we just seek a solution in this form. And unfortunately, G0 and H0 and N0 have no explicit formulas, but we can solve it in using some like mathematical maple. You can solve it, and you get this. You find a very, very good agreement, especially for the wave number, right? And this gives you a very interesting order relation. You know that the wave number is proportional to the inverse of the thickness. So this is very important insight. And also for this case, similarly, we have this scalings. We can derive very actually you can have the same scalings. Okay, the critical growth -1 is of this order, and we know that the wave number is of this order. It's large, and H0 is small, of this order, and we can derive this. Here we introduce a new parameter. Zeta is H0 by R1. It's a thickness ratio, and you can see that the critical growth is only dependent on zeta, not H0 and R1 independently. It means that it is the thickness ratio that makes a difference. And for the critical wave number, when you consider that pi H0 times n critical, it is also a function of the zeta only, right? But the latent order is dominated by this. It means that this is one of the most important parameters to determine how many wrinkles you will observe in a system. The thickness of the skin is very important. Okay, and this is a comparison, validation of the solutions. Again, you can see very good agreement. Let me conclude presentation. So we know that a stiffer film will always make an early instability, but it will reduce the wrinkle numbers. It's very important. And the soft film will generate more wrinkles after instability. And we know that a thin outer layer always produces more wrinkles. And the order is 1 by the thickness. Okay? And the grading modulus in substrate makes minor effect if the modulus decays. Okay? If the modulus decays, actually you don't need to consider the grading modulus. But if it is increasing, it will make a notable effect. So you must consider it. For curved structures, we know that curvature generates less wrinkles. A larger curvature always gives you less wrinkles. And the order is also 1 by the curvature, something like this. And we developed some analytical formulas from which we obtain these conclusions. Most importantly, we found a universal scaling law, actually not in this system. In curved system, for axial modes, for hoop modes, in homogeneous system, in inhomogeneous system, a lot of systems actually, we found that the critical stretch or critical growth is always of this order. And in this order, we know that the wave number is controlled by this. So this is actually a universal correct order. And I would like to thank my collaborators, Alan from Oxford, Angela here, and one of my former students in China. And I also want to thank the financial support from the UKRI. And all informations are included in the 2 papers. One is published, but one is submitted. Finally, thanks for your attention. Thank you very much.
All right, thank you, Yang. We've got just enough time for a couple of questions in here. So does anyone have any questions?
Kind of common question. So we did think when we started the problem, but the fact that wrinkles started to be generated before birth. So it was pure growth before the actual elephant was born. So can you say anything more about the actual role of the growth in
the role of the growth
process,
in the process? You mean in determining which? Determining
pure growth
pure
versus any other kind of conditions?
Actually, in this model, I think no, because it relies on a very strong restriction on geometry.
Mm-hmm.
It means that it cannot allow the track to be elongated too much, because elongation will release compressive stress. So there must be another factor that give the structure more stress, more compressive stress. That's why we discuss this and we impose the spring condition. But it is deserved to be studied in the future, I think. Currently, I have no very clear idea on this.
Can you say something about the experimental state of the situation? What kind of experiments are available at the moment?
For the elephant track? Actually, for elephant track, I didn't see any experiment because it's not easy to control the growth in experiments. And I discussed this with some experimental guys in different universities, but they cannot do this currently. So you need to allow the elongation and you need to control the swelling. It's not easy, I think. Yeah. But for curve structure for green morphology, okay, there are many big groups in Harvard, in Stanford. They have many beautiful experiments, but it's very hard. Okay.
Okay, we're kind of over time for questions now, so we'll leave it there and we'll make our way over to coffee. I believe you two are going to be shooting off fairly soon to continue the discussions.
Yeah, we can hang out for like 20 minutes and then...
Yeah, there you go. So we'll head over to the staff room now for some sweet coffee. So thank our speaker again.
Okay. Thank you very much.